Welcome back. Hope lunch was good for you. Next up, we have a plenary lecture by Sir Richard Roberts. Sir Richard Roberts was the Nobel Prize winner for Physiology or Medicine in 1993. Sir Robert is the Chief Scientific Officer at New England Biolabs in Massachusetts, United States. At the end of the lecture, there's a Q&A session moderated by Assistant Professor Phua Siu Cheng from National University of Singapore. You may use the microphones located along the aisle to pose your questions for the session. Sir Richard, please.
So it's a pleasure and an honor to be here to talk to you today. I'm going to talk to you about the things that I found important in my career in science. And I hope one or two of you will realize that some of the things that befell me and gave me a lot of luck in pursuing my career could also work for you too. I come from a fairly small, poor family. Neither of my parents were educated. I grew up in the town of Derby, shown here with A on it in the middle of England. And I was on the path where I lived, was on the main route to the Rolls-Royce factory in England. And at the time, it was during the Second World War, and the Germans were trying to bomb it. And they were not very accurate, and they missed the factory lots of times. But one side of the street that I lived on got almost totally destroyed, but not the one that I was on. And I realized that was when my luck in life really started. If the bomb had just gone a little bit to the left of where it went, I would not be here to talk to you today. Now, when I was 4 years old, my father got a job in Bath in the southwest of the country, and we moved down there. And Bath is a very different sort of town from Derby. It's a very nice place. If you look here, this is the school I went to from age 7 to 11. And this was where some things started to happen for me that I now realize played a huge part in my life, although I had no idea at the time. Two things happened at St. Stephen's School. One was when I used to go home at night, every so often the headmaster would give me a sheet of paper with some mathematical puzzles on him. And I used to go home and solve them and take them back, and I fell in love with mathematics because of this. And I thought he was doing it to everybody, but I later discovered I was the only person he was doing it to. So he must have seen something that I didn't know about. But one important lesson that I learned then, and one I think we could think about now, is that we have an exam when you were 11 that you took to decide what sort of school you were going to. And it was called the 11+ exam. And I took that exam without realizing it. We arrived in school one day. We were given, everybody in my class was given a sheet of paper or two. And we were told, oh, can you just answer these questions, which we did. And then later discovered this was the 11+ exam, which was to decide whether you were going to go to a grammar school or a more technically oriented school or whatever. And I think that's an ideal time, an ideal way to do exams, not to tell people you've got to swap for 2 weeks before you do it. When you take the exam, you either know the stuff or you don't. So that was very important. It was a small school. There were 4 classes and 30 kids in each class. Now, while I was there, one of the things that I did, I read a book called How I Become a Detective, and I thought this was great. So I abandoned mathematics for a while and said, I'm going to be a detective. And I was so keen on that that I really thought this was going to be my career by the time I was 10 or 11. And then my father bought me a chemistry set for school, for Christmas. And I discovered this chemistry set, you could do all the interesting experiments that you cannot do today. This was a time when chemistry sets actually had interesting chemicals in them. I learned how to make fireworks, learned explosives. Unfortunately, my parents, who were not educated, let me do it. They thought this was all fine. They had no problems with it, no idea of what I might have done. I didn't do, but I might have done. So anyway, so then I fell in love with chemistry. And this has really been the story of my life. I do something for a little while, and then all of a sudden I find something more interesting, I switch, and I do that. Now, I went to the grammar school, City of Bath boys' school. It's one of these schools where I used to have to walk to school, and to get there you walk downhill and then uphill. So it was uphill both ways. It was very good. I learned to play the violin there. I joined the school orchestra, did a lot of good things. I had a good time there. But the chemistry, which I really wanted to learn, I already knew the chemistry that they were teaching, and it got to be very boring. And so that became a little bit of a problem. So later on, you have to take advanced level examinations and so on. And when you take these advanced level examinations, we spent 1 year kind of learning all the stuff we needed for the exams. But the second year, instead of learning new stuff, they just repeatedly went over the same old stuff again. And it was unbelievably boring. And so I stopped going to school. I used to go in the morning, sign in, and then at the end leave, and I'd go and play snooker, play billiards, something at the local YMCA. And then at the end of the day, I'd go sign back into school and try to pretend, I'd been there all day. But I actually learned probably the most important lesson in my life by playing snooker. I was pretty good at it. And I was the West of England junior champion. And when I got discovered for not going to school, I thought I was going to be thrown out. And I went to audition to become a professional snooker player. And there was a guy, a world champion at the time, called Joe Davis, and he was looking for a sparring partner. They sort of go around and they do exhibition games and so on, and he wanted someone who wouldn't actually beat him, but who would make him look good. So I went and I auditioned for that, and then the headmaster decided he wasn't going to throw me out of school after all, and I always feel, I really missed what I could have done in my life to become famous. I could have been world snooker champion. That would have been pretty good, I think. So after school, I actually failed physics the first time I took it. I had to spend an extra year in order to pass physics to get to university. And I ended up going to Sheffield University. And it was, for me, the perfect place to go. It was really good. They had a very good students' union. They had a lot of good people there. And I enjoyed it very much. I got a bachelor's degree and then decided I wanted to do a PhD. And the head of the organic chemistry department was a guy called David Ollis. Oh, he's not. I thought I had the slide. And so I went to work for him. But what happened was that instead of working for him, I got put in a lab with this Japanese fellow, Kazu Kurosawa. And this is a photo I took about, 7 or 8 years ago when I was in Japan. I'd gone to see him. And he was probably the best mentor I've ever had in my entire life. He was also very, very good. And he had this trick. When he asked you to do an experiment, he'd explain why you would do it, and then explain how to interpret the results. And if things didn't work out, he'd figure out why it went wrong. And I learned so much from him. And as a result of that, in 1 year, I had all the results I needed for my thesis. But of course, England is England, and you can't write a thesis until 3 years have gone by. So he left after the first year. He also taught me how to play Go, this game on the left, which if you've never tried it, is a pretty good game. And so the second year in doing my PhD, I was trying to do experiments that I thought were good, but nothing much really worked because I didn't have Kazu there, telling me how to interpret everything and what not to do wrong and so on. And the third year, I started to spend a lot of time in the library, and I came across another book called The Thread of Life by John Kendrew, which described the origins of molecular biology. And again, it's one of these cases. I read this book, and I knew I wanted to be a molecular biologist. I didn't want to be a chemist anymore. And so when it came time to apply for postdocs, I applied to 6 labs, all of whom were kind of chemists who'd switched to things that were more like molecular biology. 5 of them turned me down. 1 of them took me. And that was this man, Jack Strominger, who at the time, when I applied, he was in Wisconsin. And I thought I was going to go to Wisconsin in order to do my postdoc. But then 2 months before I was due to leave, he wrote to me and he said, can you just delay for a couple of months because I've just been appointed a full professor at Harvard. So lo and behold, I ended up at Harvard instead of Wisconsin. And that also turned out to be a lucky thing But one other thing that happened was that Jack had a reputation of being quite a taskmaster and really causing people to work very hard. But his lifelong ambition had been to be a professor at Harvard, and he just achieved it. And so he was really happy about this, and he really let me do what I wanted to do, which was to pick up a project that a previous postdoc had started, and that was to sequence a glycal tRNA from staph epidermidis. Well, the guy who had started the project was using very old-fashioned methods. And then I started reading, and I discovered that there was a very good method that had been developed by Fred Sanger at the MRC lab in Cambridge to sequence RNA using P32 labeled RNA. And so, I talked to Jack and I said, well, could I go to Fred's lab for a little while to learn how to do it? And he said, fine. And so I went over there. This is Fred Sanger on the right-hand side, a very distinguished individual and actually a wonderful role model. He'd already won one Nobel Prize for determining how to sequence proteins, and then he figured he was going to start sequencing RNA. I went there, learned how to do it. I spent 6 weeks in his lab, came back with 3 notebooks full of stuff, how to do, and we set up a mini version of his lab at Harvard. And that turned out to be very good because a lot of people came to me to learn how to sequence RNA, one of them being Wally Gilbert, who's shown on the left here, who actually got the prize together with Fred for sequencing DNA, but that came a little later. So anyway, as a result of that, people were coming to my lab, and I made a lot of friends, and people knew, that I was helpful. And I got offered a job at Cold Spring Harbor, and this was very strange. I was in a seminar one day with Mark Potashny, who was an assistant professor at Harvard at the time, and he said, Jim Watson's going to come and talk to you and offer you a job. And I said, oh, really? I'd never met Watson. I didn't know who the hell he was. And so Mark says, yes, he'll come and talk to you. And so a couple of weeks went by and no sign of Watson. And Mark says, well, Jim doesn't actually know who you are. Perhaps you can go and introduce yourself. So I go into his office, and I say a 10-minute interview. That may be an exaggeration. I basically walked into his office. He said, I want you to come to Cold Spring Harbor. I want you to sequence SV40 DNA, and then asked me a few trivial questions. And, said, and I started walking out of the door, and he said, oh, and don't worry, but you should probably come and visit Cold Spring Harbor. But don't worry, you got the job. And this was my first real job, if you like. This was my inauguration as a PI. Anyway, so I went down to Cold Spring Harbor, and I was supposed to be sequencing SV40 DNA using RNA sequencing to copy it. But at the time, there were 2 other groups doing this, and I hate to be competitive in that sort of way. If I'd started it, I don't mind competition, but just to try and do something other people were doing. And so I decided I would try to develop a method for sequencing DNA that was based on the use of these restriction enzymes. These were enzymes that had been discovered by Dan figured out how to use it. He's in the top left. In the middle is Werner Aber, who found the first restriction enzyme. In the bottom left is Ham Smith, and he discovered the first useful restriction enzyme, which at the time was called endonuclease R. And so I went down to Cold Spring Harbor. I started to make, at the time, I think there were 3 restriction enzymes were known, so I made them. And what these enzymes do is they take DNA and cut it at very specific sites. And we know the recognition sequence, we know what they use to recognize and cut. And I figured if there were more of these, then we could use them in order to sequence DNA. And so I started making restriction enzymes. Well, to cut a long story short, that didn't actually work out. But the restriction enzymes turned out to be unbelievably useful. Everybody was interested in them. People used to come to Cold Spring Harbor meetings, and they'd have a tube of DNA in their pocket. They'd come down to my lab, and we'd set it up so that they could see whether we had an enzyme that would cut their particular DNA. And if it did, then they would say, oh, Rich, could you give me a sample of this? Can I just take a little home with me? Or they'd write later and say, could you mail me some? Or could you give me the strain and show me how I can make it myself? And it was obvious there was a possibility of making a business out of this. And so I go to Jim Watson and I say, look, everybody wants these enzymes. You couldn't get them commercially. let's start a company at Cold Spring Harbor and use the profits from selling these restriction enzymes to support the research at Cold Spring Harbor. And Jim Watson, in his infinite wisdom, said, ridiculous, you can't make money doing that, and plus it's really disgusting to be associated with a company, and he didn't want anything to do with it. And yet here I am giving all these things away. Everybody wanted them. And so I asked around at NIH, someone said, there's a guy in Boston who is interested in this, and we heard they were going to make them, and so I got introduced to them, and that is how I got involved in New England Biolabs, which I'll tell you about a little later. Now, one of the things that happened when we were hiring postdocs, I used to always give them a project to find a new restriction enzyme because we knew we could get a paper out of that. But then we'd look for a more challenging project. And this one guy, Rich Gelinas, came and started working with me. And we had the idea that it would be nice to see if promoters, the regions of DNA that tell RNA polymerase where to start making RNA, whether it was the same, whether the signal was the same in higher organisms as it was in bacteria, because both Wally Gilbert and Mark Potashny had figured out prokaryotic promoters. So we started doing that, and this became Rich Gelinas' project. We started looking at adenovirus for the simple reason that there were transcripts, pieces of RNA were being made coming in from the ends. The virus is linear. We thought if we can sequence the DNA at the end, find out where the 5' end of the RNA is, where the start point for the RNA, we just look upstream and we've got a promoter. And so we spent some time, maybe a year or so, working on that, but we couldn't get enough RNA to really do what we wanted to do. And so we switched to looking at late messenger RNA, and we knew quite a lot about the transcripts. You see L1, L2, L3, and L4. These were regions where we knew there was RNA being made. They were of different lengths, and we figure there's a load of different promoters, a load of different sequences at the 5' ends of the RNA. And if we can work out what those sequences are, we can do some DNA sequencing and then find out what precedes them. So we did this experiment. The idea was if you've got a piece of RNA, you can cut it with an enzyme called ribonuclease T1, which cuts after every G residue. And RNA, messenger RNA in eukaryotes is different from prokaryotes. It has something at the 5' end called a cap. It's a funny modification. And at the 3' end, there's a poly-A tail. And so when you cut with G, you get all the poly-A's, all of the caps, which represent the 5' end, and then all the others are just regular oligonucleotides. And so I came up with a way to separate them, and we looked at the terminal 5' oligonucleotides, these things that had the caps. And we were expecting on this plate to see maybe 15, 20 different ones, and there's only one. And so, Richard showed me the results, and I said, hey, you better repeat that. Let's do that again and see what's going on. And he did it again and again and again, and I said, look, I'll do it. I'll show you how to do it properly. And then I got the same result, and so, of course, at that point, I believed it. So we knew already there was something different about the way that adenovirus was making its RNA from the way that other prokaryotic organisms made RNA. And that led to this paper called One Predominant Undeconucleotide. There was just one oligonucleotide that was at the 5' end of every messenger RNA made late during adenovirus infection. And the question was, how is this possible? So you can think of two easy ways. One is that this is just a repeated sequence. It's all over the genome. And so the RNA polymerase binds and starts making RNA. But we did a lot of experiments and showed that that was not true. That just wasn't possible. And then we did another experiment. We would take DNA, adenovirus DNA and adenovirus RNA, and hybridize them. They form DNA-RNA hybrids. And you could treat those very gently with a ribonuclease so that you get rid of any loose RNA around, and you lost this cap. This cap disappeared. And so it said that whatever was going on, the 5' end of the RNA was not being coded next to the main body of the RNA. And so this was an explanation as to what might be going on. At the top, I've got a DNA-RNA hybrid. The RNA's got this poly-A hanging out, and it is put on after transcription. It's not present in the DNA. And at the 5' end, we thought there must be something at the 5' end that was coded somewhere other than on the DNA. And one possibility was it was a primer. Maybe there's a primer there. And several people had suggested that. And so we started to do some experiments and think about how we might test this hypothesis. And at the time, people had just discovered that you could make RNA-DNA hybrids in such a way that they form these ring structures and that they were stable because DNA-RNA hybrids are more stable than DNA-DNA hybrids. And so if that's the case, then you've got this tail that's going to be sticking out at the 3' end with all the poly-A, and there must be a tail at the 5' end. And if we could find something that would tell us where this 5' end was, i.e. if we could find the piece of DNA that was coding for it, then we could use this DNA probe in order to see what's going on. And this was the 1977 R-loop experiment. I came up with this idea one Saturday morning. Richard and I had gotten into the habit of constantly meeting on a Saturday to discuss why last week's experiments hadn't proven what we'd wanted and to think of next week's experiments. And I came up with this, but the problem was it was an electron microscopy experiment. Neither Richard nor I were electron microscopists, but fortunately, just down the hall were two really good electron microscopists. And so we went down and talked to them and said, you know, would you do this experiment? Could you do it for us? If we make the reagents, will you do the experiment? So they sort of said yes. It's, you know, no one's done it before, but it should be okay. We think it could be done. And so on the Sunday and Monday, Richard made the reagents that were necessary. And then on the Tuesday, we did the first experiments. These are the two people who did the experiment, Louise Chow and Tom Broker. And the experiment was to take the probe DNA, just as I showed you on the last slide, and then at the bottom were the results that we actually got, as opposed to the ones we were expecting. What we were expecting was that this piece of DNA would just bind at one place, but in fact, it bound at two places, indicating that somehow the RNA at the 5' end was being cut into pieces before it ended up in the messenger RNA. And this was the discovery of RNA splicing. And it was so different from anything that anybody had predicted. Nobody had even suggested this might be a possibility. And so we did the experiment. I think we had the results about 10 o'clock in the morning. Every piece on every molecule on the electron microscope looked like this. And normally, when you just get a result by electron microscopy, you don't believe it because you're just looking at a few molecules, and so you want to do more. But we'd already spent about a year and a half doing enough biochemistry to know that what we were seeing was a genuine result. And I can tell you, by that afternoon, people were talking about Nobel Prizes. People were on the phone, they were talking to people. People in other labs were busy showing that they could get the same results, and so on. Everybody trying to claim credit for having discovered it, of course. This was the paper that emerged from this. It's called An Amazing Sequence Arrangement at the 5' ends of adenovirus messenger RNA. And there's a little interesting story here that I think is quite useful. My co-authors didn't like the word amazing, and so I had to work pretty hard to get them to agree to this. They said it's not scientific, you know, it sounds like magic or something. It's not scientific. And so I eventually talked them into it, sent the paper in. 3 reviewers all wrote back and said, great paper, wonderful results, etc., but you shouldn't use the word amazing in the title. And so I got on the phone and I talked to the editor of Cell, Ben Lewin, and was talking about some of the other points that the reviewers had raised. And during the course of the conversation, I said, you know, what did you think when you first saw this? Oh, it was amazing, he said. I said, I rest my case. It's always worth talking to the editors of the journals that you try to publish in if you have some things that you want to convince them of. Anyway, so that was a very nice paper. 1977 was when the work was done. 93, I got the Nobel Prize. I shared it with Phil Sharp. Phil had also made this discovery. Actually, we think it may be a week or two after us, but he'd been operating independently at MIT. And so anyway, we both ended up sharing the prize and going to Stockholm and having a great time. And I can tell you, the parties they hold in Stockholm cannot be beaten. So I recommend it to all of you, you know. This is really a good thing. So let me tell you a little bit about New England Biolabs. So, you know, I wanted to form this company at Cold Spring Harbor and use the profits to support research at the lab. And Jim didn't want to, and so I eventually ran into this guy, Don Combe, who was up in Beverly, Massachusetts. And I called him up and I just said, you know, I heard you were trying to sell one of the restriction enzymes, and he said yes, and he was going to send it to Miles. They're just a distributor of enzymes. And I said, well, you know, we've discovered 30, I think we had at the time, at Cold Spring Harbor, and I know which ones people want. You should make them and then sell them directly, and don't bother going through a distributor. Take the profits yourself. And he had been an associate professor at Harvard in the medical school. He was in a department where they never give tenure. And he was really pissed off with the system. And he said, well, I'm going to leave university. I'm going to start a company. I'm going to use the profits to support research. I'm going to fund all of the research that we do. And I'm going to set up a company which will be Harvard and NIH all in one place. And he thinks that's what he did. We now have 100 people at Biolabs, all doing research. Pretty much all of it is basic, all paid for by profits from the company. So the original NEB that I went to when I first went up to Boston to meet him is shown in the top middle picture there. It was in a basement underneath a hairdressing salon in Beverly. There was a makeshift lab. You can see a picture of it on the right-hand side. It was all, you know, from used equipment that they got from Harvard and so on. In 1984, we put up a new building in North Beverly and then moved everybody over there. And in 2005, we put up another new building in Ipswich, which is where we are now. And I started off as their chief consultant. Don said he would give me 10% of all of sales, not just profits, 10% of all of sales. And he increased the price 10% over what he was going to charge so that he could pay me. After 1 year, it got to be too much, and I said, I just can't take this, you know, this is too much. And so then we dropped it down to 1%, and then that became too much, and then we agreed on a set fee each year. So the company did really well. Within 1 year of starting up and selling, we did $200,000 worth of business. This was back in 1975. This was the first catalog. I did more for this catalog than any other I've ever done. And this was how this database on restriction enzymes came about, because I was using the profits, the opportunity here to form a database about known restriction enzymes. Now, these are one or two of the things I got involved with after I won the Nobel Prize. On the left is so-called Dr. December. They had this calendar, fun calendar called Stud Muffins of Science, and I was Dr. December that year. I spent the money from the Nobel Prize to put a croquet lawn in front of my house because I love croquet, and it was the only way I could ever have afforded it. And the Scientific American actually wrote an article saying all the ways in which Nobel laureates, you know, spend their money wisely and the good things they do, although some people just mess around and screw it around by putting croquet lawns in front of their house. But for me, this was very good. It's been very good, and I continue to play today. There are a number of honors and things that came this way. On the right, I was a little concerned when Prince Charles knighted me because his hand was not quite as steady as you might wish. And I was really a little bit, and the sword looked really sharp. Anyway, that all went. I had a couple of things named after me. But one of the things that I've done, I discovered before I won the Nobel Prize, that I've always been a bit of an activist, and I would speak out and tell people what I think, and usually didn't lead to anything. But after the Nobel Prize, people started listening. And not only did they listen, they actually started acting occasionally. And so I decided that this was too good an opportunity to miss, And so I got involved in forming Nobel campaigns of one sort and another. And one of the best that we ever did was to get some nurses, Bulgarian nurses, out of jail in Libya. They'd been accused of spreading HIV in the children's hospital, which they hadn't done. They were on death row. Several of them had been tortured into confessing. And it was clear nonsense. And I organized the Nobel laureates. We got about 120 signatures. I went down to the Libyan embassy at the UN and talked to the people there. And eventually, I went over to Libya and talked to Gaddafi's son. And at the end of the conversation, he said, we're going to let them go. So that was one thing that the Nobel laureates can do when we group together. And it's worth remembering that grouping together is a good thing, no matter what you're doing. I also have this big campaign that I've been running for a long time now on GMOs, supporting GMOs. The developing world really needs these, and we have to do something about this. Luck and failure are an important part in science. So I learned about luck playing billiards. I played a shot and it missed, but something else happened and it worked out, and then the next shot I muffed it. And so an old gentleman came up to me and he said, well, if you ever have a lucky break, the secret is you've got to take advantage of it. Don't let that chance go away. And that's been with me all my life. Kazu Kurosawa, very lucky, Harvard, not Wisconsin, looking for eukaryotic promoters in adenovirus. I didn't know what I was going to find. We were just doing some basic research, discovered splicing. Taken an early plane. I was originally booked on the first plane that went into the World Trade Tower in 2001. And I was going to a meeting in California. It got moved forward by one day, and I ended up taking that plane. I had to change my ticket, change the plane, and I was over in California when the World Trade Tower happened, and then studying bacterial RM systems. But I want to end by talking a little bit about something that I've become very aware of recently. I think I'd been aware for some time, but not to a point where I wanted to do anything about it. And that is the way that women are really not treated as well as they should be in science. We've got a lot of really talented, wonderful women, and I would recommend reading these books. The Exceptions by Kate Zanicki, which talks about Nancy Hopkins and what happened to her at MIT. This book, Invisible Women, came out a few years ago. It came out in England, and it talks about a lot of data related to how women are not treated as well as men. And this is particularly true in the medical fields. Very often, doctors, they run trials. They run the trials on men without bothering to include women and not worrying about whether that's a problem or not. This book by Katalin Karikó, she won the Nobel Prize a little over a year ago for messenger RNA. Her story is amazing. You really have to read it. It's hard that she could ever have done the research that led to the Nobel Prize. And finally, Rita Colwell, who was head of NSF, has a book called A Lab of One's Own, which is really good. And this documentary, Picture a Scientist, is about Nancy Hopkins. But I recommend women to read it, men to read it particularly, because so often we're biased against women in ways that we don't fully appreciate. And I know from my own experience, I've done things that when I look back, I was biased against women. And I'm really sorry about that. And I want to do something about it, which is why I try to publicize these books as much as I can. So with that, I'll stop, and I thank you all very much.
So Richard, do you mind staying on the stage? Thank you for your talk. We now have Prof. Phua to moderate the session.
Okay.
So, yeah, I'm sure all of us enjoy listening to your, Sir Robert's great talk on his journey as a scientist and also in the industry, and valuable insights and funny anecdotes. Now we open the floor to questions. Anyone would like to give a go first?
Well, I guess you're going to have to ask the first one.
Okay, let me get the ball rolling then. I mean, I was actually inspired, because me as a cell biologist who then switched over to systems neuroscience, understand the challenges of, crossing towards different fields. And that's the same for you as well, right? Because your entire career spent not only molecular biology, but also in structural biology and also in computation, right? And then, so I was wondering maybe you could share some advice with our young audience regarding, how to navigate, in today's landscape, how we should, pursue interdisciplinary research.
Mm-hmm. Well, I always feel that when you find something that is more, or hear about something that's more interesting than what you're doing, don't be afraid to switch. I think so many people really say, oh, I've got to be a doctor, or my father said I got to be a doctor, or my mother said I got to be a doctor, and when it's not really what you want to do. And I think the people who are happiest in life are those who are doing what they love to do. I don't feel I've worked a day in my life, okay? My work has been my hobby. And, I find it difficult to convince my wife about that sometimes, but nevertheless, I don't feel I work at all. And so when you're a student, or when you're sort of at the early stages of your career, make sure to read around your subject, apart from your subject. Go to lectures about things that are not in your subject, because you just never know when you're going to learn something or hear of something that is so interesting, you say, I want to do that. So I was really pleased when Jack Strominger took me, because I'd heard him give a lecture about microbiology, describing his work on penicillin and the mechanism of action of penicillin. And I thought he was fantastic. He gave an hour's talk, and he must have described 200 man-years of work in that talk. And he made it all sound very easy and interesting. And so it was great to then go and be in his lab. And I had a great time there. And it was mainly lucky because he'd just achieved his lifelong ambition. He let me do what I wanted to do, which I tend to do anyway, but it's nicer if the person you're working for actually lets you do that. I didn't have the same experience with Jim Watson, but we used to fight all the time. But apart from that, it was okay. But I had a good time at Cold Spring Harbor. So yeah, and I think the other thing is, it's really important to realize that when you're doing experiments, things will fail. And failure is when you really learn. If everything works all the time, you don't learn very much. But it's when things fail and don't work. And I always get excited because I think, oh, nature's trying to tell me something, I thought I knew how this worked, and it doesn't. And this is great. Failure is really good.
One question? Okay.
Maybe.
Yeah, go ahead.
So thank you very much. So in continuation to the question, how hard did you find it was to switch a subject basically after the PhD, between the PhD and the postdoc, when all the basic training you have been through did not include biology? Mm-hmm. And how do you maybe suggest to do such transitions?
Well, as I was saying, I like to read. And I can read a book, and by the end of that book, I can become convinced of something, which is how I got into molecular biology. I mean, I hadn't even finished the thread of life before I knew I wanted to be a molecular biologist. And as soon as you decide you want to change, then you can do a lot of reading, you can find out about stuff. But again, if it's something you think you're going to be passionate about, it's easy. It's so straightforward. It's when you try to switch into something that you're not passionate about, that's when it becomes difficult. And so if you find what you're passionate about, it's easy, very easy to switch. It's easy to do anything. And it's fun, it's great. Love it. I'm getting very interested in artificial intelligence these days, so.
And just like a small addition, so at the beginning, did you feel a disadvantage compared with other colleagues in the field? How was it in terms of how you feel?
I don't really look upon my career or being a scientist as a competitive endeavor. I look upon it, I do what I want to do. And I don't like people telling me what to do. So I'm not a good student in that way. But so far it's worked out.
Thank you.
We have another question over there.
Yes, thank you so much. I want to continue in this line because, sorry to say this, but you've been in science for a long time now. Did you realize that it changed somehow? I mean, now you're saying that we need to fail, that we learn from failures, but we also have the pressure to stay in time, to publish fast, to have our grants coming in. So did you experience some change in this? And is there some hope maybe that it will go back to the good old times?
Well, I mean, there's no doubt things have changed. So the funding landscape has changed. But, you know, I would say if you really want to get worried about funding and so on, start a company and fund yourself. You know, biolabs, really, we're a private company. We've funded everything ourselves. We never borrowed any money to get started. We had products fairly quickly. We sold them. We made money. We invested back in the company. And that is easy. Now, as far as if you're in an academic situation where you have to apply for funds all the time, my goal and what I've always done is to have 1 or 2 projects that I call bread and butter projects. I know they're going to work. They're not necessarily terribly exciting or anything, but they're good enough to get a grant for. And then I use the grant money to, or at least a decent part of it, to do the stuff that's interesting, that's more fun, you know, that is, you don't know whether it's going to work or not. And if you don't do that, you will never make any big discoveries because you can't write a grant and say, hey, fund me, I'm hoping to make a discovery, right? That doesn't work. So you have to write something that looks like a bread and butter project, it's going to work, but then use at least some of the money in order to do something more interesting.
Thank you.
Okay.
I think we have time for one more question.
Hi, Professor. I'm Mark from the Philippines. So my question is something related to your response. So could you describe your overall experience transitioning from being purely academic scientist to a technopreneurial scientist? So somebody who has a business adept as well in using science for, I don't know, economic or societal gains. And would you recommend it to everyone, or do you need to have certain attitude or grit for you to become a successful technopreneurial scientist? Thank you.
So I don't consider myself a businessman. Even though I work at a company, I do basic research. Every day I do basic research. It's all computation, bioinformatics. If I've got an internet connection, I can work wherever I am, including at the back of this room while somebody else is speaking. But you can really do wonders if you really try hard to do what you want to do. And you can do it within the context of a company if you can convince the people who are running the company that what you're doing is worthwhile. And we're lucky because we wanted to support research. We always wanted to support research, and that's what we've been doing. We've been doing that. I say we have 100 people, more than 100 people in Beverly, all doing research, almost all of it basic, all paid for by the company. Worldwide, we have a little over 700 employees, but the profits, we spend them on doing research. And I think, you know, when you want to form a company, there are 2 ways to do it. One is to do a small operation yourself, or you can try and find a businessman. But the problems with finding a businessman is that they want to get into it to make money. They're not interested in the science. They want to make money. And, you know, just between you and me, I think the worst thing humans ever invented is money. Because if you look around and you see why people do things, almost every time look for the money, and that's why they do it. And that's not good. It really is not the way in which we should be driving society and encouraging individuals. They should be doing things because they love doing it. It's good for society, good for them, good for their family, not just to make huge amounts of money. I don't know what these billionaires do. Do they sit and count their money at night? I mean, what do they do? Incredible. They have way more than they need.
Okay, I guess in consideration of time, we have to wrap up because we have a following plenary lecture by Professor Brian Smith. But on behalf of everyone here, I really wish to extend our deepest gratitude to Sir Richard Roberts for sharing his remarkable story and insights today. And I think in particular, right, your emphasis on the role of computation, structural biology, and bacterial systems in driving, discovery reminds us of how, foundation science actually fuels future revolutions. So looking forward in the future, right, we now with tools like CRISPR and artificial intelligence transforming a landscape, I think your lecture really inspires us to embrace curiosity, collaboration, and also, of course, our occasional serendipitous breakthroughs as we navigate in the next frontiers of science. So yeah, let's put our hands together again to thank Sir Richard Roberts for his time.
Thank you. Thanks.